Hi everyone, welcome to our next video for week 6, where we're going to talk about a goodness of fit test. The chi-square goodness of fit, or GOF test, is used to test the claim that an observed frequency distribution fits some given expected frequency distribution. Observed frequencies are obtained from sample data, and expected frequencies are obtained by calculation. Effectively, our expected frequencies are those claimed values in our hypothesis test, and our observed frequencies are the sample data that we're comparing to it. To find those expected frequencies, if we know or are told that all of the expected frequencies are equal, we calculate those expected frequencies by dividing the total number of observations n by the number of categories k. If they are not all equal, we calculate that expected frequency by multiplying the total number of observations n by the probability p for that category. So one of two things should be given to us. We should be given a probability for each category for that expected information, or we should be told that we expect that those frequencies are all equal, that we expect that the distribution is uniform. This is a hypothesis test. So we're going to be using that same 4-step process that we used throughout all of week 5. So a quick review from week 5, we know the p-value method for hypothesis tests. The first step is we state the hypotheses and identify the claim. Step 2, we calculate the p-value using a calculator. And then for step 3, we compare that p-value to our alpha, our level of significance, and make a decision. And then our last step, step 4, we write a conclusion. We summarize our results in terms of the decision that we made and the claim that we were testing. For a goodness of fit test specifically, our null hypothesis is that there's no difference in the frequency distribution. The alternative is then there is a difference in the frequency distributions between observed and expected. When you're writing out your null and alternative hypotheses, you should be specific about what frequencies you're comparing or what distributions you're comparing. And you should use the wording that's used in that word problem. We're going to do a few examples in just a second so you can see what that looks like in terms of a real problem. For step 2, we're going to calculate our p-value. So on a TI-84, you're going to go to that stat tests menu and scroll down to option D. And there is a function called chi-square GOF test. And that's for goodness of fit specifically. In GeoGebra, you're going to use the chi-squared test, and you're going to enter the observed data first, and then the expected data second. And remember that it's asking for lists of data. So on the TI-84, you're going to need to put your data into lists before you call up that goodness of fit function. So for this, first, you're going to want to go and put list 1 should be observed data. List 2 should be expected data. For chi-squared, you're going to have 2 lists. And remember, list in GeoGebra should be the value, comma, the next value, comma, the next value, comma. So those numbers, comma, separated and surrounded by curly brackets. And you'll have 2 lists. You'll have one for the observed and one for the expected. What I typically do when I do this is I enter the list separately first and I give them a name. Oftentimes I'll just call it list 1 and list 2 because that's what TI-84 does, and that's what's in my head, but you can name them anything. And then when you go to call that chi-squared test function, it's just L1 comma L2, which is nice and easy. In this case, for a goodness of fit test, because we're dealing with 2 distributions and each distribution has a number of categories, instead of our degrees of freedom being n minus 1, the degrees of freedom is going to be k minus 1, where k is the number of categories. So you're looking at your data table. How many columns does it have? That's the k value, and you're going to subtract 1 from that. You'll notice that in the GeoGebra function call, it doesn't ask for that because it can figure it out from the length of your observed and expected list. The TI-84 is going to ask for it, and it's kind of confirmation because technically the TI-84 can also figure that out from the length of the list. For step 3, just a quick reminder, if your p-value from step 2 is less than or equal to alpha, you reject the null. And if your p-value is greater than alpha, you do not reject the null. So smaller p-values we reject, larger p-values we do not reject. So we're going to work through 2 examples, and I'm actually going to switch screens here so we have some room to write, but let's read this out first. So example 11.2 says employers want to know which days of the week employees are absent in a 5-day work week. Most employers would like to believe that employees are absent equally during the week. Suppose a random sample of 60 managers were asked on which day of the week they had the highest number of employee absences. The results were distributed as shown below. For the population of employees, do the days for the highest number of absences occur with equal frequencies during a 5-day work week? Test at a 5% significance level. And the table that they give us is sample data. So when we go to solve this problem in just a second, that's my observed data. Those are those observed frequencies that I know I need. So let's go ahead and switch screen. I can find the right screen here. Check, is that what I'm sharing with you? Yes, it is. Good news. So let's go ahead and pick through this problem. So one thing that they said, that second sentence, most employers would like to believe that employees are absent equally during the week. And that is an important phrase. That's telling me that the expected data should be evenly distributed among each of those 5 days. So the first thing that I'm going to do on this table is I'm going to add a row for the expected values. Sorry, this isn't super neat. I'm trying here. So these are going to be our expected values. And I know that these down here are my observed values. So the next thing I need to do is figure out what are my expected values. So I'm going to come back up here to this information. And I know 2 things. I know that the number of people that I sampled is 60 managers. And I know that the number of categories in my table is 5. There's 5 days during the work week. And I also know that when I see that keyword equally, to find the expected frequency for each category, I divide n by k. So 60 divided by 5 gives us 12. So I know that my expected row, each category should have 12 people in it if employees are absent equally during each day of the week. The question is now, is that true? We have this expected value, and we have some sample data to corroborate it. Do those two frequency distributions match? So we're going to go through our 4-step hypothesis method. So step 1, state those hypotheses and identify the claim. So our null hypothesis is that there's no difference between those distributions. In other words, we are saying that those absences occur with equal frequency. Our alternative is that there is a difference. And in this case, that would be not equal frequencies, meaning some days you have more people absent than others. And then we need to label one of those as our claim. And it says the results were shown for the population of employees. Do the days for the highest number of absences occur with equal frequency? This is what they're asking us to test. So they're asking us, is the null hypothesis true? So that's our claim. That's going to affect how we write our answer in step 4, but we don't have to worry about that so much now. We do need to figure out our p-value. So here's how I show my work. I know I'm going to use a function call, and the calculator is going to ask for 1 or 2 things, depending on which calculator it is. It's going to ask me, where is my observed data? So I'm going to put my observed into L1. It's going to ask me where my expected data is. I'm going to put that in L2. And it's going to ask me what my degrees of freedom are. And I know degrees of freedom are k minus 1. So 5 minus 1 is 4. And then we're going to do a function call. So if you are in GeoGebra, you are doing, I got to pull it up because I have the memory of a squirrel, apparently. Let's go back here really quick. Chi-square test. So on GeoGebra, I'm going to write chi-square test. And then observed frequencies, expected frequencies. Or if I'm on a TI-84, let's go ahead and pull up that calculator and see what it looks like. So here's our TI-84. We know to do this, first we have to put the data in the calculator. So let's go ahead and do that. Stat edit. Clear out this information. And we're going to type our observed in L1, expected in L2. So raw data in list 1, our expected frequencies in list 2. We're going to go back to stat, test, and then we're looking for chi-square GOF, which is option D. Press enter, and it asks us for 3 things. It asks us for where the observed is, where the expected is, what our degrees of freedom are. It defaults to the observed as L1 and expected as L2. So if you're doing that consistently, you shouldn't need to change anything except that degrees of freedom. In this case, our degrees of freedom is 4. So to show work for this, I'm going to copy down that function name, chi-squared GOF test, and then I'm going to copy down what it asked it for. Where is my observed? Where is my expected? What is my degrees of freedom? And I'm going to pull that calculator back up, and we're going to go down to calculate and see what that spits out. And it gives us two things. It gives us a test statistic, which we don't need for this method, and then it gives us a p-value. You'll notice that p-value is pretty big. It says our p-val is, and I just lost it, and I have no memory, 0.5578. 5578. So next step, we're going to use that p-value, and we're going to compare it to our alpha. So for step 3, our p-value and our alpha is 5%, which is 0.05. And 0.5575 is bigger than 0.05. So that tells me I should not reject. Do not reject the null. So that last step, we would write our summary. So we're going to start with our decision in step 3. We did not reject, so there is not enough evidence. And then we go back and look at our step 1. The null was our claim. So we're talking about rejecting or not rejecting. So there's not enough evidence to reject the claim that. And then we go back to that word problem and we look for information. And looking at that word problem, oops, I didn't mean to move that. Nope, I didn't mean to move that either. That last sentence says, do the days for the highest number of absences occur with equal frequency? So we would say there is not enough evidence to reject the claim that the highest number of frequencies, highest number of absences occur with equal frequency. Okay, so we're going to do another example, but my hope with that is that that process feels familiar. The actual hypotheses look a little different. The function we use for p-value is a little different. But after step 1 and 2, 3 and 4 are exactly the same as last week. And 1 and 2 are just modified, still the same steps. So this is all we're doing this week is more hypothesis testing. Let's go ahead and clear our mess here. Not so much liking the new changes to Microsoft's. Ugh, yeah, nope, not liking it at all. Microsoft made some changes to their whiteboard and I am not a fan. I've been unlucky. Okay, so let's pull this down. We have some room. We'll go ahead and move on to our next example. So example 11.3 says one study indicates that the number of TVs that US families have is distributed as shown below. And you'll notice that table gives number of TVs versus percent. It says a random sample of 600 families in the far west US resulted in the data shown below. And then it gives us number of TVs versus frequency. At the 1% significance level, does it appear that the distribution number of TVs of far Western US families is different from the distribution for the US population as a whole. So they're asking us, does this data from the far West US match the data for the whole US? Do they fit? Do they match? And before we start, we have to identify our observed, we have to identify our expected, we have to identify our degrees of freedom. I know that observed comes from sample data. So this column of frequencies that came from that 600 family, that's my observed data. So this right here is what I'm entering in the calculator. And the number of TVs are then my categories, 0, 1, 2, 3, or 4 or more. That means this overall US table must be my expected, but you'll notice that it's percent and not frequencies. I need a column for frequency. So I'm going to add a column to this table for our expected values. And when we have a distribution that's not uniform, when it's not equally likely to be in each category, remember that those expected values are n times p, where n is the sample size. We sampled 600 families, and p is that probability for each category. So for this first row, we're going to do 600 times 0.10, which is 60. Pull up this and move it off screen for a second so I can do some quick math while we're working. Our next row, we're going to do 600 times 0.16. Which is 96. Next one is 600 times 0.55. Which is 330. And 600 times 0.11. Which is 66. And then the last one's going to be 600 times 0.08. Which is 48. To check that you did that expected column correctly, those values should add up to 600. The frequencies in the observed table should also add up to 600. Last step, we need to figure out our degrees of freedom. We know for a goodness of fit test that that's number of categories minus 1. And there are 1, 2, 3, 4, 5 categories. So 5 minus 1 can be 4. So let's go through our 4-step hypothesis test. Our null hypothesis is that the far west frequencies are equal to the whole US. So the null, we are assuming that these two frequency distributions are the same. Our alternative is then that the far west, not lost. Why you shouldn't record videos this late at night. That the far west is not equal to the whole US. Those two distributions are different. And we look down here at the bottom, it says at 1% significance level, does it appear that the distribution number of TVs for far west families is different from the distribution of US population as a whole? Different from means not equal to. So the alternative is the claim that we're testing. All right, step 2, we're finding our p-value. So I'm going to do the same thing I did before. I'm going to put my observed into list 1, and I'm going to put my expected into list 2, and I know that my degrees of freedom is 4. Again, if you're on GeoGebra, it is, why did I, chi-square test? I had a brain fart again. And GeoGebra just wants observed and then expected. Or if you're using the TI-84, you're going to do chi-squared GOF test. And that wants observed, expected degrees of freedom. So this time I'm going to use GeoGebra so you can see what it looks like in GeoGebra. Again, let me see if I can find that. Nope. There we go. Yay. So let me scoot this over here just so I can see my data and enter those lists. So I'm going to create L1 for my observed. Enter, so it's saved in memory, and then L2 for my expected. And then we're going to come back over this way. And I'm looking for chi-squared test. And it needs L1, L2. And you'll notice it automatically spits out numbers once I start typing, and I get both of those lists in there. Just like last week, GeoGebra tends to do things backwards from the TI-84. So GeoGebra spits out the p-value first, and then the test statistic. And that p-value has 1, 2, 3, 4, 5 zeros, and then a 5776. So 5 zeros, and then a 6, basically, if we round that up. I have something rounds up to 6. So that's super, super small. So we can be fairly certain in whatever decision we make. And we know for our decision, we compare that p-value to our alpha. And our alpha is 1%. So 0.01. 0.00006 is definitely less than 0.01. So in that case, we feel fairly confident in rejecting the null hypothesis. For step 4, we start our sentence by looking at step 3. We rejected the null, so we do have evidence to we do have enough evidence, sorry. So there is enough evidence to and then we go back to 1 to determine support or reject. And since our alternative is our claim, we're talking about supporting or not supporting. In this case, there is enough evidence to support the claim. And then we would go back and look at the wording in the question. So does it appear that the distribution number of TVs of far Western US families is different from the distribution of the US population as a whole? So we would say there is enough evidence to support the claim that the distribution number of TVs for far West families is different from the US population as a whole. Okay, so let's pop back up to our slideshow here. We already went through that. If you have any questions on what you just saw or anything in a previous video, feel free to let me know via email or drop by office hours Tuesday, Thursday, Saturday. Again, I've only had one person stop by office hours, so they are vastly underutilized, and I promise you're not bothering me if you drop in. So please use those if you have questions. Otherwise, I will see you in the next video.